all this potential energy and all this stuff. Who cares? To figure out who cares, I can tell you, Castiglione cares. So who is Castiglione, and if Castiglione cares, why should you care? Let's take a look. Okay, this is the guy Castiglione, Carlo Alberto Castiglione. Okay, and he was an Italian, lived between 1847 and 1884. He was like 47 by the time he passed away. Actually, less than that, 37 by the time he passed away. Just 37 years old, right? He was a railway engineer. He wrote a dissertation in 1873 entitled Intorno ai sistemi elastici. You can say there's something to do with elastic systems, and intorno tells you, I mean, it's actually about elastic systems and equilibrium of elastic systems and forces in elastic systems. He worked for the Northern Italian Railways, and he wrote a very interesting theorem which is called Castiglione's first theorem, and it's a very complicated statement. The first partial derivative of the total internal energy in a structure with respect to any particular deflection component at a point is equal to the force applied at that point and in the direction corresponding to that deflection component. It's a lot of words. Bottom line is, if you differentiate the potential energy with respect to the kinematical parameter, you will get the corresponding value of the force, right? So basically, force is the derivative of the potential energy. You might have known about it. If you don't, this is actually originally stated by Castiglione in this form, but for a particular purpose. People had already had some idea about it, but he really took it very far. By the way, even Castiglione, when he mentioned force, it may mean either force or couple moment, and displacement may mean either translation or rotation. So it deals with everything that we deal with, not just ordinary displacements. Okay, so this is a very general result. Okay, so what? The main thing is here. The redundant reaction components of a statically indeterminate structure, which is mechanism, are such that they make the strain energy a minimum. So what happens is, you don't have to find all these blocking forces and this, that and the other. All you have to do is find the strain energy, which is what we call the potential energy of the system, and find its minimum. If you find the potential energy and find its minimum, you don't have to worry about all the internal forces. You don't even have to draw a free body diagram. It is just mind-boggling. It's so good. We still use this all the way to find out what kind of proteins. Even in drug delivery, this is one of the things that people are using to find new drugs. They want to find out how different kinds of proteins fold and how they interact, and all of it is based on extensions of this idea. It's really a remarkably powerful idea. Okay, so what we are going to do is, we now have an alternate way of finding out things, which is the following. We can find equilibrium configurations of systems. If I have a mechanism, where will its equilibrium configuration be? So first step, find the potential energy as a function of the kinematical parameters. We did that already. Second step, differentiate and set equal to 0, because there is no net force when it's in equilibrium, right? So Castiglione's theorem says derivative of the potential energy is force. In this case, derivative of potential energy is 0. You can check that it's an extremum by taking first derivative. If you take second derivative, you can show that it's a minimum. We will worry about that later. All we have to do is differentiate it, set it equal to 0, and find the value of the parameters. That will give you equilibrium configurations. You don't have to worry about constraint forces. You don't have to do equations of equilibrium to find equilibrium. Can you believe that? Right? No body force, no vectors even. Joy. I mean, there's nothing here. Isn't that remarkable? That's the beauty of calculus. That's why we care about it. We have converted all the way from a geometrical approach and vectors to calculus. The thing is, it works only if the mechanism can move. If it cannot move, you cannot do it. That's why we did statics in a different way. Okay, there's another theorem which you can do for statics, and you learn that in a later class, because it's Castiglione has another theorem which is called, I noticed that the first one is called Castiglione's first theorem, right? The second one is called Castiglione's second theorem, and it's more advanced. And that's what allows you to do statics. Interestingly enough, moving objects are simpler than stationary objects in this version. Okay, so off we go. We'll try and figure out how this works for our example problems, and then you will see what's the beauty. Okay, let's start with the first one. Oh, we already did this. You remember this, right? So let's complete this thing. We already found the potential energy. So this was Y, and we already found the potential energy. Total potential energy for this was Wy plus half K Y minus Yf squared, sorry, Lf squared. That was my potential energy. Now I want to find out what's the equilibrium configuration. If I did force balance, you can easily see that it will compress. W over K. Let's see if we get the same result. Differentiate potential energy with respect to Y. Will give me W plus K times Y minus Lf equal to 0. So that gives me, so remember this is delta, that's how much it deflects, which implies delta equals minus W over K. Can you see that? I got it. No FPD, no equations of equilibrium. Works. Castiglione's first theorem. If it's a structure, you still have to do the same thing. It works for mechanisms to find the equilibrium of a mechanism. You don't have to do anything. Okay, this is a boring one. You could have done this even with a free body diagram. So now let's look at the next one. If I gave you this problem in an exam and I told you find me the angle at which this whole thing stays at equilibrium, and then you had to do this, you would say, oh shoot, there is no 2 force body, there's nothing, I gotta draw a lot of free body diagrams here and find all kinds of stuff. Right? It's going to take you like 2 hours. But now we have a very simple setup. We already got the potential energy of this, which was what? Let's make sure it's 100 times 2 cos theta minus Lf whole squared minus W times 2 sin theta minus Bf. Plus Bf. Bg. Remember this was G. Okay, that was our version, right? So now I'm going to take dPe d theta equal to 0, and you will get 200 times 2 cos theta minus Lf times minus 2 sin theta. I'm just differentiating with respect to theta, minus 2w cos theta equal to 0. Solve for theta to get equilibrium. It will tell you where to stop. Isn't that amazing? That's all you have to do. Of course, solving for this is a pain in the neck, because I got like this multiplication of sin theta and cos theta, and then I got cos theta. It's really a headache. But if you have with calculators, you can do this very easily. If you have a graphing calculator or something, just graph this function, see where it goes to 0, and that's the answer. You don't even have to do that. You can actually graph this function, graph PE, locate minimum. How about that, eh? Because engineering wise, engineering wise, I want an approximate value for theta. I'm not that keen on getting whether theta is 47.7 degrees or 47.6 degrees. I want to know, is it 47 degrees, 50 degrees, where is it going to stop? Right? It's extremely beautiful and simple setup. Okay, now let's try one more. We already saw this one. The potential energy for this. The potential energy for this was very similar to the potential energy for the other one. So let's see what this was. This was 9 times 4, 9 times 4 cos theta minus LF whole square plus W times 4 sin theta plus H. Remember, this H was this. Okay. That's the total energy. Again, partial PE with respect to theta equal to 0 will give me what I want, and that's pretty easy. Will give me again 18 times 4 cos theta minus LF times minus 4 sin theta plus W times 4 cos theta equal to 0. Done. Solve this angle for theta and you'll be able to find where will this stay. If I had this spring and this much mass, how far will it descend? You can find that. Isn't that amazing? That's the beauty of this. Now let's look at another problem. What if up to now we have seen only springs and gravity? What about external forces? Our trick is actually a very interesting trick. We treat external forces like gravity, controllable gravity. Treat the external force as a dead load. What do I mean by dead load? Load of fixed magnitude and direction, just like gravity. Okay, except it's not always pointing down, it's pointing in whichever direction the load points. So total potential energy is potential energy of spring plus potential energy of gravity minus work of external dead load force or moment. How much work will the dead load do? So how do I know this? This is force times distance. So I'll tell you precisely what it is. Work of dead moment, torque, is moment times angle. Work of force vector is not force times distance. It is force dotted with position vector. So it is F dot R where the F acts, not F times D. Okay, so for this particular case, you have to find the position vector. There is no way. In some cases, it might be easy, but generally speaking, so you need to find the position vector of the force as a function of the kinematical parameters. Otherwise, you cannot do this. Let's look at an example. Here's a very interesting one. I got a piston cylinder mechanism. There's something pushing here. Let's call this point A. So sorry, A, B, C. Sorry, oh, that was A. So this is B. So let's call this point C. Okay, oops. Okay, so now let's do this. What's the potential energy of the system? Equal to PE spring. I'll always write this and cancel out the things that I don't want. Plus PE gravity minus work of P minus work of F. Right? So the work done by this force will go here. The work done by this force will go here. Okay, so in this particular case, PE spring is 0, PE gravity is 0. So now I got minus WP minus WF. So that's pretty easy. Let's find that out. So P is minus P times J. W is F is minus F times I. Those two things are obvious. Okay, so now I got to find the coordinates of P. Rp equals L cos theta in the I direction plus L sin theta in the J direction, or F equals 2L cos theta in the I direction. Obvious to you? So now WP will be, take the dot product and it will turn out to be very easy, minus PL sin theta. Of course, you could have seen force times distance traveled by it is that much, and then WF equals minus 2L cos theta. Now you are pretty much done. PE total equal to minus PL sin theta minus 2FL cos theta. To find equilibrium, partial PE with respect to theta equal to 0, which will give me minus PL sin theta minus 2FL cos theta equal to 0, which implies tan theta must be equal to 2F over P. That's the angle at which it will stay at equilibrium. Right? You can do this by doing free body diagrams and so on, but you'll be here forever. I want you to understand the beauty of it. So let's summarize. What's our basic idea? Find the degrees of freedom and kinematical parameters, also known as generalized coordinates. If there are springs, find the length of each of the springs in terms of the kinematical parameters and use that to find PE springs. If there are heavy objects, find the height of the center of mass of the heavy object as a function of the kinematical parameters. Use that to find PE gravity. If there are external loads, find the position vector of the external loads as a function of Kp and calculate W loads, which is F dot R. Then you do PE springs plus PE gravity minus W load. Differentiate this with respect to the kinematical parameters. Solve for them. By the way, even if you have more than one, it will still work. You have to do partial derivatives. That's it. This 4 or 5 step sequence you have to remember. Memorize that. It is extremely useful for you to deal with any mechanism. So whenever you think of mechanisms, there have to be 3 things that you have to think about: kinematical degrees of freedom, kinematical parameters, potential energy, and then you will be in very good shape. Thank you very much.